Today we'll be looking at the problem called dice combinations. This is a pretty interesting dynamic programming problem. First, let's start by looking at what we actually want to do. So the instructions are that our task is to count the number of ways to construct a target sum n by throwing a dice one or more times. Each throw produces an outcome between 1 and 6, which is just a standard die. The example we're given is if our target sum is 3, there are 4 different ways, which include either rolling a 1, 1, and a 1 to get a target sum of 3, rolling a 1 and then a 2, rolling a 2 and then a 1, or rolling a 3 right away. If we roll anything above a 3, obviously that doesn't constitute part of the solution for n equals 3, because that way we would be exceeding our target sum. So for the input of the problem, we're only given one integer as an input, which is our target sum. And what we want to output is the number of ways that we can reach that target sum, modulo 10 to the 9th plus 7. The reason why we want to do the modulo is because for larger sum combinations, we might encounter integer overflows in certain languages. So we want to be taking the modulo at every step of our computation. And the constraints are that n has to be lower than 10 to the 6th, which is actually a quite large number. The example we're given is the same as the one that was described above. For a target sum of 3, there are 4 different ways to reach the target. So first, let's go over what the most naive or brute force approach to solving this problem would be and why it won't work in this case. So a naive solution to this problem would be to basically create a recursive function which takes as input initially our target sum, and then it computes the number of ways to get to that sum by recursively calling the same count function on all predecessors of the target, which are in the range of no more than less than 6. Because if we have a target sum of 8, for example, then we're only going to be summing the ways to get there from the recursive subcalls of 2, 3, 4, 5, 6, and 7, because if we have a 1, then we physically can't roll a 6 in order to get to the 8. So I think a good approach would be to code up the naive solution and see why it doesn't necessarily work in this case. Let's say, again, we have an input of 3 as given in the problem, and let's code up the naive solution that we just described. So we're going to create a recursive function called count, which will take the target as an input. And the base case in our case will be that in order to get to a sum of 0, you only need one step. So if n is equal to 0, then we are going to return a 1. The other case that we have to account for is if we're getting a negative number as an input, which could potentially happen from the recursive calls, we have to return a 0 because it would be impossible to reach the target sum. That was the case that I described with if we have initially a 1 and we try to reach an 8, there should be no ways to do it because the maximum we can roll is a 6. So if n is less than 0, then we are going to return a 0. Then what we want to do is initialize a total variable, which will be what we return in the end, in the case that we don't encounter the base cases. And again, what we're going to want to do is iterate through all values that are no less than 6 from the target that we're finding. So for r in range 1 to 7, which will include the 1 and not include the 7 because the top of the loop is not included in Python. We're going to increment the total by the number of ways for each of the subsequent 6 possible steps we can roll. So we're going to be adding count of the n minus r, which is what we're trying to find. N is the initial input and r is the roll that we are currently rolling. So that means if our initial input was an 8, initially the r is going to be a 1. So for the case of 8, we're going to add the total of getting a 7, which is 8 minus the first roll. For the second case, we're going to be adding the count of 6, which is going to be 8 minus 2. And we're going to be doing so, we're going to continue this until we reach the last possible number, which can give us an 8 after one roll, which is going to be a 2. The last iteration is going to be r equals 6, and we have 8 minus 6 is equal to 2. At the end, we will return the total. And now let's take the input that we have and simply print the result of calling our recursive function on the input. So let's see if this works. Yep, so for the case of a small input of 3, we do get the correct output of 4. And now let's try increasing our input and see what happens. So let's say we have an input of 10. That still works. Let's say we have an input of 15. Still works. Let's say we have an input of 30. At this point, it's taking a while already because at each step we have to create we have to create 6 recursive branches for the call. So even for a small input of 30, we can see that our function is already starting to get stuck. And the real reason for why this is so inefficient is because if we think about it, we're recounting, we're doing duplicate work in the sense that for a large call, we keep calling the function count on the same duplicate number. So for example, if we start with an 8 and we're calling this count on a function of 8 minus 1, 7, we'll still be making the same recursive call for previous calls, if that makes sense. Maybe that wasn't the best example, but a better example would be if, say, our target sum initially was an 8, and then let's say we're in the middle of this R loop and we're trying to find the count of 4. Whenever we're trying to find the count of 7 in the sub-branch of the 8, we'll also be calling count on 4, which is a lot of duplicate work. So even for a small input like this, we already get stuck, and it's way too slow. Look at a visualization of the recursive call branch. So again, let's say that we're trying to find the number of ways to get to a 7. We'll be making a recursive call for all numbers in the range of at most 6 less than 7. So we'll start at 1, 2, 3, 4, 5, and 6 and sum up all those ways. However, at each of those subsequent recurrent calls, let's say for example for a 6, we'll also be computing the number of ways to get to a 1, a 2, a 3, a 4, and a 5, and so on. So that means we're doing a lot of duplicate work for each of the branches. And while this might not look terrible, if we have a larger number like 30 and there's 6 branches at each single node, that creates a ginormous recursive tree, which will take forever to solve or exhaust all our memory. So again, the more optimal and good approach to solve this problem is to instead use a bottom-up dynamic programming approach, where instead of going down from the target, we actually build up our solution by going through an array. Excuse me, let me just fix this up before we start. So the way we want to do it is to create an empty array initially of zeros, and where each index will correspond to the target sum that we're trying to reach. And what we'll do is we'll start iterating and fill it up according to a set of rules. So again, at index 0, we'll have the target sum of 0. At index 1, we'll have the target sum of 1, and so on. Once we have this initial array, which represents the number of ways to get to a specific index or the target sum, we want to start considering the same base case which we had in our recursive approach, which is that to get to a target sum of 0, there's only one way to do it, by not rolling any die. Then the way we want to be filling in the rest of the array is by going through it and summing up all the possible ways to get to the previous numbers, which are no less than 6 from the target that we're trying to approach. So in order to get a target sum of 1, there's only going to be one way to do so, and that is going to be by starting off with having a target sum of 0 and then rolling a 1. For the target sum of 2, we follow the same exact approach, and we see that in order to get to a 2, we can either roll a 1 from the initial number of ways to get to a 1, or we can roll a 2 from the initial target sum of 0. So again, for the 2, we're going to be adding the 2 previous elements in order to find the number of ways to get to a 2. For the case of 3, which is the one that we're given in our test case, we should be getting an output of 4, and the way we build it is, again, we can either start at a target of 0 and then roll a 3, so that'll give us one way, so we're going to be adding this value to it. we can either get a target sum of 1, which we already know there's one way to get to it, and then we can roll a 2 to get to the 3, or we can get to a target sum of 2 and then roll a 1. So again, for the 3, we're going to be adding all previous elements in order to find the value. 1 plus 1 plus 2 is equal to 4. We're going to keep up with the same exact approach and add all previous elements up until we reach the maximum value of 6 from this starting point. And since we're not yet at the target sum of 6, we can just simply add all previous elements. So for a target sum of 4, we're going to add 4, 2, 1, 1, and that'll give us an 8, I believe. Yes, that'll be 8. For 5, we're going to be adding 4. We're going to be adding the 8, the 4, the 2, the 1, the 1. This will give us 2, 4, 8, and 16. Oops. And we'll do the same for the 6. Let's just go through the cases until we get to a target sum of greater than 6 to see that we don't just add all previous numbers, but we actually add the last 6 numbers after the target that we're trying to find. So again, for 6, we're going to add all of these numbers together to give us a 4, an 8, 16, and a 32. And for the 7, now we will see that we can't actually add this initial 1 because there's no way for us to get from a target sum of 0 to a target sum of 7 without rolling just one single die. So for here, for the 7, we're going to be adding only these last 6 elements. And basically what we need to do is keep iterating until we reach our target sum because no other computation is needed. And the number that will be left at the index of the target sum will be the answer to our problem that we're trying to return. So again, we see that for a target sum of 3, there's 4 different ways to get there. Now let's move on to programming our dynamic programming approach. The first thing we'll do is take the number as input. Let's go with the example test case to start off. Sure that we have it correct. Yep, we get back a 3. Then what we're going to want to do is define this initial array which we will be populating, and what we want to do is start it by filling it with zeros and then putting the first element as 1, which is the target sum of 0 and will be our base case. So we will do we will need n plus 1 elements because it's a 0 indexed array. And the first element will be the target sum of 0. And so, for example, if we need to find a target sum of 3, we need an array of length 4, so n plus 1. Let's make sure we have that array correctly. Yes, we do, an array of 4 zeros. Then we're going to want to set the first element to be a 1, which is the base case that we were talking about to get a target sum of 0. And then what we're going to do is have a double loop approach where the first loop will be iterating through the elements and populating, and the inner loop will be going through and summing up all previous elements up until a value of 6 away from what we're trying to find. And obviously for smaller elements, we're going to need to check and make sure that we don't go out of bounds on the left side of the array. So the outer loop is going to go through elements in res. So for I in, we'll be starting it off at 1 because we don't need to populate the first element, which is already populated. The second inner loop is going to contain the possible dice rolls which we can do to get to that target sum, which is going to be no more than 6 below. And we're going to be doing for roll in range 1, 7. Again, the top bound is not included, so that's why we have the 7 here instead of the 6. We then need to check that we're not going out of bounds on the left side of the array, so we can do that by, here, let's change this to index. We can do this by comparing, checking if the index minus the roll is at least equal to 0. What I want to do is simply add the index minus the roll count from the array to the current index that we're trying to calculate for the target sum that we're at. So we're going to do res of index is equal to the current count of the index plus the number of ways to get to the previous number, which is index minus the roll for this iteration of our loop. And actually what we're going to want to be doing at every single step of this calculation is taking the modulo operator in order to avoid integer overflow issues. And the modulo that we need to take is 10 to the 9th plus 7. So we're going to do mod 10 to the power of 9 plus 7. And that should be it for our solution. So if this condition doesn't hold, it means we are out of bounds and we're simply going to continue to the next roll because we can't add a sum that's negative from our array. So let's have a look at what the res array looks like and see if we have everything correct. Oh, actually, we made a little mistake. Oh, yeah, so the mistake we made was that we set the second element to be a 1 instead of the first element. So this has to be a 0 because based on our visual solution, only the first element was initialized to a 1, which is our base case. So now that that's fixed, our array should look correct, yes. And then so if we're trying to find the target sum of 3, we look to the third index of the result array, which is going to give us the answer of 4. Since we don't have to output the entire array and we just need to output the single target sum, at the last step, we're simply going to take the res at index n to give us the correct answer. That looks good. And now let's also see how this dynamic programming approach won't get stuck at a larger input like 30, unlike our initial naive recursive approach. So that is a very large number, but we get it almost instantly for a very large input. Let's go ahead and try to submit and see if we pass the hidden test cases. Yep, all cases passed. Thank you for watching.